Hi folks, see you speaking again. In the previous video, we established the principle of operation for a monostable circuit working with a PLC. It was a bit easier to do because we used instructions in programming. Today, we're going to discover the magic of the TTL monostable. So what was the monostable? You press a button and you determine the pulse whose duration you can calculate. And this is what we're going to do today with the TTL circuits, and it's going to be done in 3 steps. One step, the first, is going to be doing the wiring to establish the circuit itself to make it working. Second step is going to do the inner work of the monostable. How is this actually working? How can we discover the inner work of the monostable using the timing charts? And the third part is going to be putting it in some applications. Let's start it. Come closer. So here is a simple breadboard, a very small one. We don't need more than that. And we're going to use just few parts in order to find out how is this operating. So the package itself is this one here. It's only having 16 terminals. That model I have in my hand right now is 74LS123. There are several TTL packages containing monostable circuits, and I'm going to focus right here on some of these packages. We have a package called 74122. It can be found in different flavors with LS and others. This one contains one monostable. So inside that package, you're going to find one monostable. I preferred to focus on another package called 74123. And this one, the one we are going to discover today together, is containing two monostables in one package, 16 pin package. It can be found as the original 74123. I have one somewhere here in the box. This is a original 74123. This one you've seen before is 74LS. So I write it down, 74LS123. You can have also 74HC123, which is a, remember, high-speed CMOS, but having exactly the same pinout as the TTL123. Remember what is the difference? The original and the LS, they have the power supply 5 volt. The HC has the power supply between 2 and 6 volts. So if you energize it at 5 volts, it's going to work exactly like the original TTL. Of course, you are going to be able to find the HCT 123. And for all these, in order to calculate the duration of the pulse, we're going to say here the pulse width. There is a formula. Who established the formula for that? The designer of the inside schematic. And any manufacturer providing that kind of package is going to deliver us the formula to calculate how long the pulse is going to be, the one we can control. And the formula is 0.33 RC. What is the resistor? What is the capacitor? We have it right here. This is the resistor and this is the capacitor. We're going to discuss that soon. And this is the formula for it. And you also have an equivalent in the CMOS. If I pick up an example here, CD4538, be careful because this one also contains two monostables in a 16-pin package. It does exactly the same job as the 123 here, exactly the same job. with two major differences. Don't forget, because it's a CMOS circuit, the power supply is going to be anywhere between 3 and 15 volt. That's another story, but if you energize it at 5 volts, it's going to work like a TTL. Two major differences. The pin out, not the same as 74-123. So you cannot interchange these two packages. So you have to consider that. And the formula for the pulse width is simply RC. It's a bit simpler. So it's not 0.33, it's RC. How do I know that? If you go in the documentation, in the PDF delivered by the manufacturer, of course, you're going to find the formula. So we focus today on this one, on the TTL, the 74-123, but don't forget, it has a CMOS equivalent, which is 4538. Okay, let's go to do the wiring. In order to do the wiring, we have to see how the package is organized. In the original notation of the manufacturer, even if I'm going to use exactly this one here, which is printed black and white to do the wiring, because it's easier for me to focus, okay? If we take a look right here to see how the manufacturer organized the package, remember the package 123, which is right here, and you are going to find this one, of course, on the Google Drive. It contains two monostable circuits inside. I have here a red dotted line. Whatever is on the left, this is the one shot number one. One shot is the same as monostable. And whatever is on the right side of it is the one shot number two. So the manufacturer attached notations, and whatever you see in red are notations related to the monostable number one. So this is the input A, this is the input B. Why the manufacturer provided two inputs? Because they said you can trigger the monostable, in other words, the pulse at the output. You can trigger it on the falling edge or on the rising edge, as you wish. So either this or that. Of course, we cannot use both at the same time, but one at a time, you can trigger either falling or rising edge. It also has a reset, and the reset is acting on the falling edge. So if you don't want to use the reset, you're going to hold it in high logic. It's a very user-friendly package because the ground is on the pin 8 and the VCC 5 volts is on the pin 16. The output here is called 1Q, and the numbers in red here are representing what's belonging to the one shot number one. So 1Q represents the normal output of the first monostable. Respectively, 1Q bar is the complementary output of the first monostable. C bar is because the clear or the reset is active 0, and 1C means it belongs to the one shot number one. And here is the external capacitors. So the capacitor and the resistor controlling the duration of the pulse have to be connected outside of the package, obviously. And here is where you're going to connect the capacitor, and here you're going to connect together the resistor and the capacitor. So all this belongs to the monostable number one. And similarly here with other pin numbers, you are going to have the same input A but belonging to the second monostable. Here the input B belonging to the second monostable is working exactly like this one here, but is for the second monostable. Here you have a reset, is acting low exactly like the other one, like the other reset, but is on the pin 11 instead of the pin 3. And same thing about the capacitors. The capacitor and the resistor establishing the duration are between the pins 6 and 7. So now you can take a good guess. The numbers in black out of the package are representing the pin numbers around the package. Okay? So I didn't put them in the order we expect on the package 1, 2, 3, up to 8, and then 9, 10, 11, 12, and so on up to 16. I put them in the logical order because you can see here there are identical structures for both monostables. Now the key factor for this, and it's better to, in order to put notations, to return to this black and white drawing here. So in order to get it right, take a look what we do. We have to realize what is the key for that to work. Here inside we have a JK flip-flop. You are going to discover the JK flip-flop. I have it in an older video if you look in my collection. The key here is on the clock input of the JK flip-flop, you have an AND gate. So this is an AND gate. And what is the principle of the AND gate? I'm going to recall it very quickly for you. In order to get the output a 1, you need to get all these inputs here one logic. Or in order to prevent confusion, because you already have ones in other places, 1A, remember, is the input A of the first monostable, but the one outside the package is the pin number. So to prevent this, I'm going to use the letter H from high logic. If any of these inputs, they go 0, it doesn't matter what the other two inputs are doing, because 0 times anything else is going to be a 0 here. So in order to get a 1 here on the clock input of the JK flip-flop, what do we need? We need all the inputs of that AND gate to be one logic. And this is the principle of operation for the reset, for instance, or clear, because it usually stays 1. If it stays 1, it allows the other two inputs to operate. But as soon as you press the button here to make it a 0 or you connect it to the ground, a 0 here is going to prevent the other two inputs to operate, so the clock is going to stay 0. It's very easy to understand, but this is how it's working. Now, how this input called A is working on the falling edge? Simply because it has an inverter here inside. I don't know if you remember that. Usually the bubble was at the output of the inverter. Don't worry, the bubble is at the input, because they use the negative logic for the inverter here. You should not be bothered by that. It's an inverter anyway. So what does it mean? If you need the high logic here at the input, you need the low or a 0 logic. This is why the signal at the input A has to be triggered low, because when it becomes low, the output of the inverter becomes 1, so the condition is good in order to get a signal at the output of this AND gate. Okay? That being said, before doing the wiring, let's find out what are what you can use as typical values for the capacitor and the resistor. Let's do a very quick calculation. I'm going to do it right here. To take an example, if I take as example here for the pulse width, remember 0.33 RC. If I'm using for the resistor 30 kilo ohms, and for the capacitor I'm going to use 100 microfarads. If the resistor is represented in ohms and the capacitor in farads, which are the units for the resistance and capacitance, you are going to get the duration of the pulse in seconds. So let's find out. The pulse width is going to be 0.33 times 30 kilo ohms. I can write 30 kilo ohms like 3 times 10 to the 4 ohms. How do I write the capacitor? I can say 100 times 10 to the negative 6, because it's the micro. Now, if you notice here, 0.33 times 3, this is approximately 1. 100 is actually 10 to the second power. 10 to the second power times 10 to the negative 6 is 10 to the negative 4. And 10 to the negative 4 times 10 to the 4, they cancel each other out. So practically, you get the pulse width approximately 1 second. So this is going to be the trick. If I connect here 30 kilo ohms and here 100 microfarads, I'm going to get about 1 second. Instead of this, if I connect, for instance, if the resistor goes 120 kilo ohms, what does it mean? 120 is approximately 4 times 30 kilo ohms. So instead of having 1 second, the pulse width goes approximately 4 seconds. So now we can do wiring. I pick up the package from inside. It's right here. Remember, it has to be positioned with the notch identifying the pin number 1. Okay. I'm going to put it to the left over here. I put it along the slot and I press it. Okay. Next, I'm going to pick up, let's dump the components here. I'm going to pick up a red wire for the positive. I have a positive here in the top, and I have another one here, just in case if I need it. I'm going to pick up the ground right here in the bottom. Okay. The only thing I pre-wired are the 2 buttons here. For the 2 buttons, if I'm using a logic probe, my logic probe shows a 0 when I don't measure anything, so the tip is in the air, floating. So this is the limbo state. And anytime I'm going to get the letter L is going to be low, so I measure it here. So here I have a low. In other words, this is the way I'm going to use it over here for the input B. So when I press this button, we take a look, it's low. And when I press the button, it's going to become high. So I'm going to get a 1 logic. Okay? And on the other button over here, if I'm going to pick up a wire from here, it's already high. So if I press it, it's going to become low. So with this one here, I'm going to get a falling edge. And with the other one here, I'm going to get a rising edge. Okay? So that's how I'm going to do. Very easy to wire this one. After you wire the power supply, the next thing you care about is the reset. Because I don't want to use the reset, I'm going to keep it high. So, because I'm going to use 2 monostables, I have 1 reset on the pin 3 over here. I'm going to connect it to the positive. And I'm going to have 1 in the top, 9, 10, 11. So the pin 11, as you can see it here, I'm going to connect it to another plus over here. So I took care of the 2 reset pins. What is remaining? To control the inputs. So if I really want this one here to get a rising edge, I'm going to connect this on the pin 2. I'm going to connect on the pin 2. What do I do with the other one? Remember, the condition for this gate AND to operate is to have the 3 inputs here high. So to get a high here, the input 1 has to be grounded because I cannot use both inputs at the same time. I only have to pick up 1. So I picked up the input B, which is on the pin 2. So the pin 1, I pick up a wire. I'm using a kind of color codes, blue or black for the ground. So as soon as I see it here, I know this one is going to represent a low. This is the pin 1. And I'm going to do the same at this moment. I'm going to do something similar. I'm going to use for the other monostable, I'm going to use the other input A. So for that reason, I'm going to connect a wire from here. So I'm going to use the input A on the other one, which is on the pin 9, right here. Okay. And what am I going to do with the input B then? Remember, the condition for these AND gates to operate, they need high logic here on all the 3 inputs. This one is already connected to +5. And this one I have to connect to +5 because I'm not going to use it. I want it to be disabled, but actually active. So this is going to be the pin 10. The pin 10. This one here. And I'm going to connect it to +5 over here. Good. So since I connected it to +5, now I can connect the other input here over the button. I connected it to the pin 9. the only remaining components to connect now are the outputs and the network resistor capacitor, because these monostables are based on a very simple fact. The duration actually is taking through a certain resistor to charge this capacitor. And I don't want to forget to specify it here. The positive of the capacitor is going to be toward the resistor, so toward the resistor. For that reason, the other leg of the capacitor is going to be the negative, And when you use a capacitor which is electrolytic, like this one is a 100 microfarad capacitor, the negative is marked with an arrow and is written even the negative here. So the terminal closest to the mark is the negative terminal, so the other one is positive. So then I'm going to use for the first monostable a 125 kilo ohm, which is approximately 120. This one is going to be between the pins, as you can see, 15 and the positive. So that's easier for me to mount first the resistor. So then it's going to be the resistor connected to the positive. So the capacitor is going to be with the negative to the pin 14, negative to the pin 14, and positive to the pin 15. This one is connected. Now on the other one, I'm going to have something similar. Remember, if I put here a 125 kilo ohm, is 4 times bigger than 30 kilo ohm. So I'm going to get anywhere between 4 and 5 seconds. Why I don't have exactly 4 seconds? Because the electrolytic capacitors have a certain tolerance, so they are usually bigger than the value written on the body. If you want a more precise capacitor, you have to use these kind, the droplet shape, which are tantalum capacitors. These are more accurate and they have a low leakage. For the couple of seconds I'm going to use them, the leakage doesn't matter for me. So, to not forget, I'm going to connect the two LEDs I have on the normal output, pin 13. I'm going to connect this one on the LED, a limiting resistor of 1 kilo ohm, like this. And I'm going to connect another 1 kilo ohm on the pin number 5. Pin number 5. Anyway, here. 5. Good. And from the pin number 5, from the resistor, I need to go to the LED. Very well. So the only remaining things are the resistor here from the pin 7 to the positive. So pin 7 to the positive over here. And the capacitor, which is going, remember, the negative is marked on the body. It goes on the pin 6. So pin 6 to 7. So the job is done. Now what's going to happen? If I press this button here, the blue one, as soon as I press it, if I'm counting, it's going to last around 4 or 5 seconds. Let's count again. 1, 2, 3, 4, between 4 and 5 seconds. And if I press this one here, what resistor did I mount? I mounted a resistor of 220 kilo ohms. This is approximately 7 times higher, than the 30 kilo ohms. So when you press this button here, let me see what's wrong. If there is anything missing, in order for it to work. 5. Yeah, the capacitor was mounted between the pins 5 and 7 instead of 6 and 7. So now we fixed the error. It's going to last about 7-8 seconds. We're going to count them again. So 1, 2, 3, 4, 5, 6, 7, 8, 7-8 seconds. Okay? So this one is working, is exactly this one here on the rising edge, this one on the rising edge. And the other one is working on the falling edge. Now, what's interesting about that, because this one is working on the falling edge, and the pulse given at the output Q right here, on this pin 13, the pulse is going to look like that. So from here to here you have about 4 seconds. Take a look. When the pulse is ending, you're gonna get a falling edge. What if I'm linking now the output Q to the input 9, so I disconnect the input 9 from here. I disconnect it from the push button I have over here, and instead I connect it to the pin number 13, which is the output, okay, over here, which is the output of the first monostable. And I'm going to do something more interesting. I'm going to remove from here the 220 kiloohms, and I'm going to replace it by 30 kiloohms. So what's going to happen? The duration of this pulse is going to be about 1 second, okay? So let's find out, like that. So take a look now. When I press this button over here, because the other button, if I press it, does nothing. Why? It's disconnected from my circuit. But I press the blue one. I have to give it power, sorry. Now I should have reset it, but because the resets are disconnected, they are connected to the positive. The resets are not working right now. So take a look. I press the button. This one is going to last 1, 2, 3, 4 seconds. And then it's going to trigger the other one, which is lasting only about 1, 2 seconds. Take a look. Sorry, I cannot trigger from here. I have to wait until the first one is ending. 1, 2, so about 1, 2 seconds. What's happening is, at this moment here, I cascaded 2 monostable circuits, and this is why I preferred to use that package containing 2 of them, because if you think a bit, that's exactly the same principle applied several times in your washing machine, where several timers, several monostable circuits are cascaded together to perform the operations. So in the moment you press the start button on a washing machine, first thing happening, the motor starts to revolve. Couple of seconds later, when the first monostable ends, the water pours in, and when the tank is filled, it's going to be the end of this monostable, the second monostable, and then the motor is going to go back and forth to start washing what's inside, okay? And after a while, the muddy water is going to be removed from the connection, and so on. So everything is going like combining, actually cascading several monostables together exactly like here. And I can do this in another way. I can remove the 30 kiloohms. I'm going to put back the 220 kiloohms. Take a look what happens when I trigger it. The first one goes about 4 seconds. And the second one, of course, now is going to go 7 times longer than 1 second. So it's about 8 seconds, 7, 8 seconds. Okay, so it's going off. I can make it shorter also because I have 2 components inside. Not only I have resistors, but I have capacitors. So if I remove that capacitor here, which is 100 microfarads, and I'm going to place this one is only 22 microfarads, okay? So I place this one instead over here, and this way, because it's 5 times shorter, 7, 8 seconds divided by 5 is about 1.4, 1.5 seconds. So take a look what's going to happen. This one is going to last 1, 2, 3, 4, about 4 seconds, and this one is going to last no longer than 2 seconds, okay? Because I can also play with the capacitor, not only with the resistor. So this is where the formula I had right here, because it contained both components, resistor and capacitor, I played with the resistor, now I played with the capacitor, so you can play with both. So if you know the ratio between the original value you put first and the second value, of course you can very easily recalculate what is going to be the new duration, and you can control it by just playing with these two components, either with the resistor or with the capacitor, as I was showing you. And again, you've already seen a very simple application of this, because you can cascade monostables to trigger two distinctive actions one after other. And now, because we're here already, I can show you already a very useful application. In a couple of videos, you are going to have very well described the diagram of my beloved logic probe, the TTL logic probe. And what happens here is not only about measuring the logic states with the display itself. If you notice, this kind of display has two dots. It has one on the left side and one on the right side. I cleared them both, you see? And then, if I measure any low signal, like I put it at the ground right now, it shows low, but the right dot, it goes on and it stays. So what happens is, it doesn't matter how long was the pulse coming in. In the moment it's coming, here is a circuit, I put a label over it, it's written 123. It's actually 74 123. And you can see here the two capacitors, which are pretty similar to the tantalum one here. The color won't matter because they can put any kind of ink color on it. Mines are blue on the logic probe. And here in the experiment, I have a kind of light brown color, okay? Something between light brown and orange. So actually, I'm using here a 123, generating two distinctive signals, one for the low signal and another one if I measure the, take a look, I'm going to clean it. And when I measure the positive is a high logic, but at the same time I have a pulse coming here. What is this useful for? If you have to wait for a pulse which is coming at irregular intervals, you'll never know when this pulse is going to come, and you go away because you can't stay there with your eyes on the logic probe. You just leave the logic probe connected where the expected pulse is coming, and if the pulse came during your absence, you are going to find this dot already lit. What does it mean? It means you had the pulse you expected, okay? So this is extremely useful to troubleshooting, and the pulse, whatever is the duration of the pulse coming, it doesn't matter how short, I'm going to generate a constant pulse with one of my two monostables. So then the pulse coming from here is going to be recorded into a memory, which is over here, okay? When I'm going to have this diagram described, you're going to see. And then I can erase it anytime I want, and I can restart my measurements, okay? So this is one useful application. And I have another one for you for today, another kind of application. So before the application itself, because we are already here with the wiring, I want you to see now how is the, in the step number 2, how is the inner work of this monostable circuit, regardless if it is the first one on the left or the second one on the right. Both of them are working identical way, just the pin numbers are different, okay? So I prepared for you here already the 4 possible situations you may have this one working, okay? And it's a very simple relationship here between the inputs and the output to see what happens, okay? We can also put it here on the screen. See? So this one, because you have all the colors, you are going to find it on the Google Drive. Situation A. Situation A here is saying I'm using the switch A connected on the input B. What is the input B? The input B says I want to trigger on the rising edge. This is the input B. In order to use the input B, which is the pin 2 on the package, okay, which is the pin 2 on the package, I need to keep the input A, which is the pin 1 on the package, down. So the condition is A should be 0. Why should it be 0? because if I pick it up again, why A should be 0? Because A is right here. So when A is 0 connected to the ground, is going to give a high logic at the output of that inverter. The inverter is internal, is inside the package. Okay, so this outline represents the border around the package. So this is why you need to keep the input A grounded if you want to use the input B to trigger, because the input A grounded, after the inverter you have a high logic. Okay, so this was the condition. So because of this, as soon as the input B or the pin 2 is going to go up, high logic, you are going to trigger the output. So the output goes out of the stable state. This is why it's called a monostable, because it only has one stable state. In that situation is a 0 logic. And it goes out of this stable state for a while. For how long? For the formula we know already, 0.33 RC. And then it goes back to the stable state. This is why it's called one shot, because you give it one pulse, it gives you one shot in return. Or it's called the monostable because it's only staying in the stable state, and you take it out of the stable state when you trigger for a limited duration. Okay? This is one situation when you use the input B. Now, what happens is, if you trigger it several times, you cannot connect this input to be triggered over a clock generator. You have to trigger it the second time after the duration is done. Because if not, you have the situation B, which is over here. You trigger the circuit, is exactly the same situation as here. So I didn't put the condition anymore because you know it now. So now you trigger the circuit over here. So the pulse is starting and it should last exactly the duration in red. But if another pulse is coming because you trigger it again before the duration ended, what happens is everything else is erased and the circuit restarts a new cycle. So if you keep giving it pulses too often before the duration ends, before the pulse width ends, what happens is that output is going to continually remaining in one logic, so is never going down. Okay? And you have to avoid this, and now you know how, because the next time you want to trigger the circuit is only after the pulse width ends. Third situation, you don't want to use the input B anymore. Now you want to use the input A. The input A is on the falling edge. So what is the condition then? The condition then is the input B has to be kept active, so the condition is the input B should be one logic. And this is exactly what I used initially on the second monostable. And when you do, triggering on the falling edge, you're going to get exactly the same thing at the output. The duration is going to, the duration of the pulse is going to be exactly the same, 0.33 RC. And the fourth situation is what happens if you have a long pulse, let's say 1 minute, and you decide to reset. I took the same example as here because you know it already. As soon as you press the input B, the pin number 2, as soon as you press it, then when the input goes up, you trigger the output, okay? But if before the pulse ended, you press the reset, the output just goes in 0. So the rest of the pulse, supposing it was lasting 1 minute, if you press it after 40 seconds, the last 20 seconds are going to be removed. The output goes in 0. This is the principle of the reset, actually, because the reset means bring the JK flip-flop inside, down in 0. Okay? So these are the 4 potential situations that package can be working. Okay? So it's very easy now to understand, because you had the step number 1, doing the wiring around the package to see how it's operating. That was the step number 2, to find out what is the inner work of the monostable in any of these situations, triggering the input B, triggering the input A, applying multiple pulses before the pulse ends, and what happens when you apply the reset. These are the 4 situations. And now let's find out another application I prepared for you. I'm going to cut the power, I'm going to disconnect this one because this was just a very quick experiment we've done together. So we disconnect from here the logic probe, we don't need it anymore. We remove the wiring, not required. We remove the components, we put them back in the box. Okay, everything goes back as it was. Be careful when you remove the package to not fall the terminals. Okay, everything goes back. Okay, and now I have another application already prepared for you. Okay, we apply power. And here is the problem. We have a counter on 2 digits, and when you apply power, it doesn't start from 0. It shouldn't be a big deal because we have a reset button over here, so you reset it, and then you can count either up or you can count down as you wish, okay? But any professional counter should start from 0. So I stop the power, I put the power again, now it shows a 7, you know? So, of course I can reset it, but it's a bit bothering, you see? Now it's showing 99. One of the applications, one of the beautiful ones of a monostable circuit is what I call an automatic power on reset. So anytime the power goes on, automatically the counter starts from 0. So what am I going to do? Before I'm showing you the diagram, I'm just going to connect this wire over here. And around the package here is a package called 74LS123, and I only need to use half of it. I'm going to use this half. And take a look now. I shut the power down. I power it on. It shows a 0. Hey, it may be a coincidence, right? I shut the power down. 0. I shut the power down. 0. It's always starting from 0 now. You see? Very quickly. Let me just draw it for you here to see how to do it. So, if I have the package over here, 74-123. Yes, I'm going to have the VCC, pin 16. I'm going to have the ground, pin 8, ground, okay? So this is the plus 5 volt. Then I'm going to have the pin 1 connected to the ground, so it's always active. I'm going to have here the 2 pins 14 and 15, the resistor and the capacitor, positive, negative, plus 5 volt here, okay? And I only want to give it, I don't know, 1 second. For 1 second, remember, I have a 30 kilo ohm here and 100 microfarad, okay? And here is the output. I'm gonna figure it here, the output. So for the output, I'm going to use the pin 13, the output Q. The key here is the pin number 2. Don't forget the pin 3, which is the reset or clear, is going to go to plus 5 volt. Here is the key. I'm going to have a resistor and a capacitor over here, plus 5 volt. And if I put a 2 kilo ohm here and a 4.7 microfarad over here, is only taking, in the moment I put the power on, is only taking a couple of milliseconds before this capacitor is going to be charged through the resistor of 2 kilo ohms. So in the moment it's reaching a high logic, because that's what it needs, it is a high logic, it's going to trigger the circuit automatically when the power goes on. Now, how do I manage to use the output to reset? Because I also have somewhere a manual reset. I cannot connect both signals to the counter because they are going to interfere with each other. So for me, I'm going to use a exclusive OR, but you can use an OR gate, is going to do the job as well. Okay, pin 1, 2, and 3. This is a 4070. Okay, the package 4070. I don't put a power supply because you know it is the pin 7, the ground, and 14, the plus. And here you get the reset for your counter. So you can either use the automatic reset coming when the power goes on from the 123, or you can use a manual reset anytime you want, because if you keep counting over here, okay, you want to reset it, you can do it anytime. But when the power goes on, you need the automatic reset coming on. So for the duration 1 second, you can make it shorter if you want. For the duration 1 second or whatever is the duration you make for the monostable, the counter won't be able to operate. And anytime you want to make it like 0.1 second, it's gonna go so fast, the counter is practically ready to work. So that's a nice application to use for a monostable. This being said, thank you very much for today. We're going to continue with the monostables next time. Bye-bye.